So, good afternoon, everybody. Thank you very much for all those that are here and all those that are logging remotely. Today we have the pleasure of having Professor Alexander Ling from the CQT, the Center of Quantum Technologies in Singapore. Professor Ling is a principal investigator at CQT, and he led the team that developed the Spooky 1 satellite that finished over 2 years of experimentation time in low Earth orbit, right? So he's an authority in quantum optics and optical implementations, and especially with Earth-space connections. So it's really a pleasure to have Professor Ling here. He was very kind to accept my invitation to participate here. It was not so easy to find a good date, and at some point we were thinking of bringing him here physically, but it didn't happen this time because of COVID issues. So anyway, he's so kind to be here, even though it's already evening for him in Singapore. So thank you very much again, Alexander. And yes, please proceed. Okay, it's a pleasure to have you here. Thanks.
Thank you, Leandro, and thank you everyone at TII for attending this talk and inviting me to share some of the concepts and results that we've been working on. Some of you may also know that James Grief, who's one of your colleagues that used to work with me, and he's been telling me a lot about the great stuff you guys are doing there, and I really look forward to visit sometime soon. So in today's colloquium, what I'm going to do is I'm going to share with you some of the concepts of how we could build a quantum network that spans the globe. And how we're going to do that is to use small satellites. And I'm going to try and motivate the talk by discussing what are the first kinds of applications we can see from a quantum network. And then later on in the last part of the talk, I might share some results from our small satellite, Spooky 1. And Spooky 1 is a new class of satellites. They go by various names. They're called nanosatellites, or they're called CubeSats. And this photo that you see here is a picture of Spooky 1 as it's leaving the International Space Station. And the astronaut usually takes a photo of which satellite that's leaving as a visual record. And they share it with the experimental groups that developed the satellites. So without further ado, let's get started. Let's think about why we want to have quantum communications on a global scale. And in particular, what kind of quantum communication application are we going to be thinking about? And so the main motivation that's driving a lot of this work right now is actually quantum key distribution, where we want to have quantum safe communications. Last year, the Quantum Threat Timeline report, which keeps track of progress of quantum computers and how that could impact encryption, released a report, an update. And inside this report, you could see the opinions of various experts that are working on quantum computing. And with respect to the likelihood of a quantum computer breaking the encryption standards that we use today, like the RSA standards in 24 hours, this is the likelihood and estimation of some of the experts. And they can see that within about 20 to 30 years, most experts agree that such a machine capable of breaking encryption that's used today would be possible. Now, you might think that 20 to 30 years is actually a long time, and that you don't have to worry about it until it actually becomes a reality. But the fact is that, information that is being exchanged today on the internet can be recorded. And if you are exchanging information that is of great interest to parties that would like to crack this information even 30 to 40 years in the future, then you have to think about this, because the threat timeline can be short, much shorter than the amount of time with which you need to keep that data secure. So if you're in charge of thinking of this problem, you might want to start, moving the encryption standards that you use today to something that's resistant to quantum computers. So this is the main motivation that's driving a lot of this work. And of course, beyond quantum key distribution, we're also thinking of general quantum communications, where you would like to, link up quantum computers or quantum sensors. And this is really the steps towards what we call a quantum internet. But of course, in the first application, we're going to be looking at quantum key distribution. Now, I mentioned interchangeably quantum key distribution and quantum safe communications, right? But the main point is that in our communications today, we want something that's resistant against a quantum computer, right? And when we're talking about quantum safe communications, we need to have a model in mind what we're actually talking about. So the easiest way to think about it is to think that you have a message, which we call the plain text, that we want to distribute over an open channel, and anyone can access this open channel and can read what's being transmitted. So the ideal way to do it is that you want to have a key, an encryption key, which is a string of random numbers that would be mixed into this message. And then when it's transmitted in the clear, people who don't have this key cannot actually decipher it. And so in this way, if only the parties that are going to do the communications and control the key, then they can enjoy something that's nice and safe. And in some cases where you're doing one-time pad encryption, where the size of the key is exactly the same length as the message, then you have something which people believe to be very, very secure and is completely immune against computational attack. The main challenge is how you're going to actually distribute this secret key, right? And in the past, we would trust couriers, right? You can have people, driving vans around that distribute the keys, or you can even, distribute this key by tying it to the leg of a pigeon and you fly it off. The whole point is that, if this transfer process of the key cannot be intercepted by your opponent, right, then you actually enjoy some kind of security, and you can even be quantum safe. Now, the idea of physical security, usually is not very scalable, right? If you have to have a person who is driving the van around all the time, it's not very scalable, and you'd like some way to make use of the communications infrastructure that we have today, right? And this is something that we would like to do. So in terms of making use of the communications infrastructure, right, since the 70s, people have developed mathematical techniques for key distribution. And these kinds of key distribution techniques go by various names, right? The first 4 lines in this table show key distribution algorithms that are commonly used in today's internet. They form an infrastructure, actually. And this is called the public key infrastructure, where using a mathematical technique, you can actually distribute some sensitive information. And this sensitive information could actually be also secret keys that are used in other communications techniques. For example, in the last 2 lines, you have this AES system, right? So today's communication systems rely on encryption that is at various levels. There's a public key system, which is based on complicated math, where you have a one-way function, where you can distribute a public key, but others cannot guess what the private key is. And then you can actually have also symmetric key systems, where you have the same key at the communicating parties. How you choose to use which algorithm depends on where you sit in the communication stack, because the public key systems, the PKI systems like RSA or ECC, they can be computationally intensive. And so if you have lots of data that you want to transfer over very quickly today, you use a symmetric key system like AES, right? And what's interesting is that from theory, we know that if you have the algorithms and you have a quantum computer that is actually powerful enough, you can actually remove the security that some of these algorithms provide. Looking at the last column, right, on the right, on the table over here, you can see that in the presence of a quantum computer, the RSA and the ECC algorithms actually do not give you any security. And this is actually a challenge, because they are actually used to distribute a lot of the symmetric keys that we are employing today. So this is actually a very important point. Now, what can we do? What we can do is we can try and replace these algorithms right, that is being used to distribute the secret keys. And there's two methods by which we can do that. We can research for new mathematical algorithms, and this is a class of effort known as post-quantum cryptography. Or on the other hand, you can actually try and use quantum signals, do actual quantum communication to actually distribute the secret key. And so this is actually where we are sitting at, with today's technology. We know that a quantum computer will be built. We know that it can actually, remove the security that we enjoy in our communications today. And we have to take active steps to ensure that communications in the future will actually, be quantum safe. And we have two methods to do that. Either you take a mathematical method or you rely on quantum physics. Now, before I go on further, I'd just like to take a breather here, right? And see whether anyone in the audience...
One question, Alex.
Yes.
One question.
Do I have to press something?
No, just
Okay.
speak close to the microphone.
The 0 bits in quantum computing, what does it refer to?
It refers to, the amount of, how should I put it this way? It refers to the amount of security, right, that the algorithm would give you in terms of, in the presence of a quantum computer. So what it's trying to inform you is that, from the known algorithms, the RSA and the ECC family cannot protect against a quantum computer in the sense that they can be broken given some time. And so this is the way in which the NIST standards was trying to, inform the reader when they published this table. So this is actually their way of doing it. And if you look at AES, the symmetric systems, look at the last two rows, you see that in the presence of a quantum computer, their estimate is that some security is still afforded, right? In the sense that what you should do is you should double the size of the symmetric key when you're employing these AES systems. So this is the message that the NIST community was trying to make when they published this table.
Thank you.
Yeah, I also have another question. You phrase like this as like a dyadic choice between like computational security of like post-quantum algorithms and then like physical layer security based on like the quantum primitive and QKD as we know it. I mean, what is about like other ways to achieve physical layer security? For example, like using correlated randomness in mobile communication channels.
Right. That's a great question. But I guess the promise of the quantum security is that it's a temper evidence system, right? If you were to implement the QKD appliances correctly, then you can be assured that the error rates that you see are actually traceable to tempering. So it's a temper evidence system. And so this is a new capability, I would say, that I think most classical security methods cannot really provide. And it provides a very strong level of assurance when we talk about trying to secure at the hardware level the communication security. I hope that answers the question. The main difference here is that it's temper evident. Okay. I think we can move on, and so along the way, I will actually also take a breather, and we can invite questions as well. Okay, so I just want to re-summarize some checkpoints, right? One of the main things that drive our research is that the understanding that encryption key distribution is a critical enabler for a lot of the communications that we are using today, especially if we want to keep that communications private. The other thing is that not all classical algorithms are considered broken in the presence of a quantum computer. We are trying to identify post-quantum cryptography algorithms, but even the ones that we already have today, for which we have standards, can still be quantum safe. And for example, the AES 256 system, which is based on symmetric keys, is something that's quantum safe. And this is going to be very important as we talk about how to merge QKD with existing crypto systems. Because if you have a quantum key distribution system that can actually generate symmetric keys on both ends, you may actually want to use it for supporting an AES system instead of doing one-time pad. And so the point is that the one-time pad encryption technique that is often discussed in literature is a very nice idea, but I think it's going to remain a niche application for the foreseeable future, simply because the rate at which we are distributing data and information through the internet, right, is so much faster than what single quantum detectors can actually operate at. And so this is actually one of the bottlenecks that we see. And so we think that combining QKD with AES is actually one of the more natural ways going forward. And so the other thing to remember for the audience is that there is a competition organized by NIST at the moment to identify post-quantum crypto algorithms. And finally, as I start to talk about quantum key distribution, please keep in mind that there's actually a family of protocols of how one can actually use quantum signals. And in my talk, I'm going to actually choose the family known as the discrete variable family, where you actually transmit and detect individual particles of light that we call photons, right? And this is the main class of family that I'm going to talk about. And in particular, I'm going to talk about one flavor of the discrete variable family that employs entanglement. So let's take another look at QKD at a glance. How do we actually implement it inside a wider system? So as I've said, AES is considered to be quantum safe. And so if you have lots of data that you want to pipe through the clear public channel, what you do is you put your plain text combined with the AES. The AES system will actually encrypt it and then transmit it. And on the other side, an AES system that has access to the same key can decrypt the message. What we're talking about is putting quantum appliances at a very low level, at the physical layer, allow them to exchange quantum signals, generate the quantum key, which is going to feed into the AES. And so this is how we actually see quantum key distribution being deployed. Now, quantum key distribution, of course, is not just about the transfer and detection of the quantum signals, but there's also a lot of back-end communications that has to take place. Over here, I give you, a bullet list of activities that need to be done in order for the appliances to actually, come up with a secret key, right? And only two of these actions are actually quantum in nature: the exchange of the quantum signals and the measurement of the quantum signals. Once you have measured the quantum signals and converted them into a binary string of ones and zeros, then this is where a lot of the other activity takes place, where the two parties, which we often call Alice and Bob, that would actually have to compare the measurement choices that they've made on the particles. They need to estimate the error rates, perform error correction, remove any information that has leaked out to the environment through the error correction steps. And in the end, they have to take steps to remove that information leakage. And in the end, you actually will have a small set of secret keys that you can actually use. Now, the important thing here is that the blue bullet points, these are classical communication problems, right? And very often in the early literature, this was not actually taken care of. But nowadays, as we begin to approach maturity, we are fully aware that the software aspects of QKD also have to be taken care of, right? And so there's a lot of classical programming and optimization that's involved in QKD as well. Now, I'm not going to talk so much about that, but it's just something that we have to keep in mind when we discuss how we actually build QKD systems, because the back-end communications can actually be quite heavy. And so one has to make sure that there's appropriate data budget for the QKD appliances. Now I want to talk about the classic, QKD protocol, the very first one that was invented. It's called the BB84 protocol, invented in 1984 by Bennett and Prasad, hence BB, right? And the basic concept is seen in this picture, which you can actually get from the internet. It's a really nice picture. You have Alice, who's doing the transmission of the quantum signals, and you have Bob, who's doing the receiving. And what Alice does is she prepares individual single photons, and then she prepares them and sends them over to Bob. Now, when I say prepare, this means that she can put some setting into this quantum, into this photon. And in this picture here, we are using polarization, right? And it turns out that polarization is also something you can use in appliances because it's actually very, very easy to operate with. So the important thing, though, is that Alice and Bob must operate in something known as a polarization basis, right? Which means that they must choose settings of polarization where in one, if you choose the settings, if you cross the setting you cross the measurement settings, you don't get any information about the encoding that was done in the other setting. So when I talk about these settings or this basis in polarization, I'm talking about the rectilinear polarization basis, more commonly known as horizontal and vertical polarization, or it can be in the diagonal basis, or more commonly known as plus minus 45-degree polarization. And so Alice and Bob must work in this settings, right? And so Alice would choose to encode in the settings, and she transmits them, and Bob would do a measurement. Now, the important thing is that Alice must choose and encode the settings randomly, whereas Bob must send the photons into his measurement apparatus randomly. So randomness is very important. And in the original BB84 formulation, Alice and Bob have active entropy, right? They have an active choice in the transmitter side, and they have an active choice on the receiver side. The real trick comes in the fact that it's only a single photon that's being transmitted over the channel because of the no cloning theorem. If an eavesdropper were to replicate Bob's setup and put it inside the quantum channel, measure the outcomes, and then retransmit a single photon down to Bob, what's going to happen is that she's only going to guess what Alice is transmitting half the time. And so when she transmits information to Bob, she's going to get half of them wrong. And so when Bob is doing his own measurements and he's comparing a subset of his outcomes with Alice, they're going to see a very high error rate. And this is why we say that quantum key distribution is temper evident, because if anyone is trying to temper with the quantum signals, the error rates will be unacceptably high. Okay, so this is the real idea of how QKD works. The table at the bottom is showing you some idea on how you actually encode ones and zeros, right? And so what Alice and Bob need to do is they need to identify the polarization state of the photon with a 1 or a 0, right? And you'll notice that Alice is not sending ones and zeros. She's just sending quantum states. So she's not sending a message over to Bob. What's happening is that Alice is sending a random string of ones and zeros, and Bob is choosing some of them correctly. And then through a process of communication back and forth, they will agree on a final string of ones and zeros, which is common to both of them. Okay, so it's also very important that when we talk about quantum communications with people outside the field, that we make it clear that this is a key distribution technique, and it's not about encrypting information in a quantum signal. So the BB84 prototype algorithm is a really beautiful and easy to understand one. But there are certain challenges with it, right? For example, to this day, it's very difficult to get true single photon sources that can be put into appliances very easily. And so very often people, would actually use a laser, right? And then they attenuate the laser pulses to approximate single photons. And then they have to take care of the fact that there's a statistical process that some of the pulses may still contain more than one photon. And this they will call the decoy states. And they need to ensure that all the statistics of the pulses being transmitted from Alice to Bob are also respected, right? And in this way, you can actually ensure that your pulses that you're transmitting over to Bob, although they have more than one photon, could actually still enjoy the security promised by BB84. And so, BB84 in the single photon sense or in the decoy state sense, they're all known as prepare and send protocols, because there's always a transmitter preparing the state and then sending it over to the other side. Now, there's also another class of QKD protocols employing discrete variables, which can be thought of as a server-based system, where Alice and Bob are either transmitting information to a central server, or a central server is transmitting quantum signals to Alice and Bob, right? These protocols are actually more amenable to building a network, right? In the top idea, the top graphic at the which I'm showing, the basic idea there is to do a Bell state measurement in the center. So if Alice and Bob were to be able to time the transmission of the photons correctly, you can actually do a Bell state measurement in the central server. And through this way, carry out a quantum key distribution protocol. This is known as MDI QKD, measurement device independent QKD. There's some technical reasons why it's known as that. More recently, people have started doing something called twin field QKD, which can extend the range of this distance. But the real challenge is that you need to do the timing of the information between Alice and Bob correctly so that the two photons will arrive at the same time. The other approach is that you would transmit signals out. And in this approach, usually you will use entanglement, where you will have entangled photon source that typically produces a pair of photons, and then you can transmit them out to Alice and Bob. And then Alice and Bob would then actually, write down the time of arrival when the photons arrive at the detectors. And then by comparing that, they can actually, identify, which detection event on the left was, corresponds to the detection event on the right. This is, in my opinion, a little bit more near term, because you don't have to worry so much about the timing information. As long as you are, synchronized to an external clock, like on GPS or something, you should be able to, do the time tagging correctly. So the real motivation, or let's say the real focus in my group, is to take this approach, right, and to use entanglement for quantum key distribution. And we take the basic entangled photon systems, right, like what you see in this photo over here, and generate the best quality entangled photons that we can generate, and then we try and study how they can be used for entanglement-based quantum key distribution. So this is the main focus of my group's research, and this is what I'm going to be talking about for the rest of this seminar. Now, in the server-based QKD system using entanglement, the little yellow boxes where you hold the measurement apparatus, they look exactly like what Bob is using in BB84, right? You have a beam splitter, and then you would send the photons either to the rectilinear or to the diagonal basis. The difference, though, in my opinion, is that when you're doing entanglement, the random number generator, which makes a choice of which measurement detector you go to, doesn't have to be an active choice. It can be passive. And if you take this approach, then you can actually have a QKD system where the sources of entropy are almost completely passive. And so in this way, you don't need an extra quantum random number generator that you need to validate and trust. You will just use the entangled photon source, right, with its highly correlated, but non-entangled or completely entangled and random outcomes, and you transmit it over to the detectors, and then you would just split them randomly, for example, by using a 50-50 beam splitter. And so this way you can have a QKD system whose requirements on active random number generators is actually very, very low. Now, I just want to give you a cartoon of how this works with entanglement. There's no sound. I'm just going to talk over it. And so the idea is that, you know, if you had...
Alex,
Yeah?
sorry. We have one question here.
Okay, go ahead.
So I don't understand. I mean, I think I understand what you mean by active and passive. So active and passive. So you said passive would be I just put a beam splitter and then I get like a 50-50 split, right? Passively, but still quantum mechanically. But and when you say actively, what do you mean by this, and how would you even distinguish this if I don't know if somebody is doing an active choice or a passive choice, right? Because if I look after the signal at the signal after beam splitter, it looks pretty random to me, right? If the beam splitter is working properly. So what is this more a philosophical thing, or is this what does this mean, even active and passive?
It is not. It's not philosophical. It's actually a concern about how would you validate your entropy that you're using, because in the end, your encryption key is a string of random numbers, so the entropy must come from somewhere, right? So if you were to use the classic BB84 protocol, where you have an optical switch on the transmitter side, you need to make an active choice of which photon you're transmitting. So this requires an input from a random number generator. And on this side over here, they will also require an input from a random number generator. So this means that apart from just the lasers or the single photon source that you're transmitting and the detectors you have to build up, you also have to take care of the fact that you need a quantum random number generator working in the background,
And
working at the rate at which you are transmitting the signals.
And I would record this in the end for the comparison in the end.
You also have
Right?
to record.
I would
that.
record which switch has been chosen randomly, which state. Okay.
Yeah.
Fine. Okay. In the other case, this is not necessary. I don't record anything. I just get a split, and that's
Yes.
enough.
That's right.
And can you explain why this is the case? Is there like an intuitive explanation if you now go from the BB84 to the entanglement-based one, why you don't need this activeness anymore?
Right. So I guess the main point is that if you think about it, the transmitter definitely doesn't need an active random number generator because it's just an entangled photon source. And then if you look at the detector setup, right, there's really no need to, because if there's an individual photon coming in, it looks at the beam splitter, for example, and it makes a choice whether it goes to the detector setup at the top or the detector setup on the right. Okay. Now, you asked a very good question. Why is it in entanglement you don't need to do it? You don't need this active choice. Actually, I should make this point clear. Even in BB84, you don't need this active choice. You can just use a passive beam splitter. Right? It's just that in the past, people have often felt that they needed to keep track of the randomness of the entropy choices that they were making. But I think actually with entanglement, you don't need to. And in fact, if you think about it, probably for BB84, you don't need it either. Okay?
Alex?
Yes?
But pardon me. I mean, you still, sorry, if I understand correctly, when you vary the choice of measurement basis, that's what allows you later to detect the presence of an eavesdropper, right?
That's right.
So are you saying now that you don't need to vary the measurement basis and still have unconditional security, or am I getting it wrong?
I think that's what I'm saying. You still have to vary the basis, but you let it be a passive element that varies the basis.
Okay. You still randomly choose which basis to measure, right? Okay,
Yeah,
sorry.
you still do that.
Okay.
Because
Okay,
imagine
thank you.
you replace this random number generator with just like a 50-50 beam splitter.
Right.
Then there's going to be a random choice of measurements as well.
Okay, excellent. Thank you very much. Yeah.
But in BB84, there 48. Sorry.
BB84.
There you would need a record of this. Actually, I don't see how this could be done by passive choice.
I think at the transmitter side, definitely you need a record of it, for sure.
Yes.
Yeah. On the detector side, they just have to see which detector clicked, and then they will know which way
Okay.
the
Okay.
photon went.
Thanks.
Okay, these are great questions. So I'm just going to quickly go through this animation, right? And the idea is that over here, you have an entangled photon source. And for simplicity, I'm going to just show that the measurement settings has a bunch of rotating wave plates. Now, this is, of course, active, right? It's an active choice. It's not passive. But I think, we developed this algorithm or this video for the public, and it was just it's easier to talk to the public that way. But essentially what's happening is that you transmit these entangled photons with a strong correlations. You send it to the detectors, and the detectors are going to choose the basis. And when you have the correct basis or measurement settings, you will actually have the same outcomes of zeros and ones. So you see, what they have to do is they have to compare the settings and then choose a subset of strings, right? Which give you the same outcomes. Now, what happens if there is disturbance in the system, or if there's an eavesdropper who's trying to actively tamper with these entangled photons and then replacing their own signals inside? What's going to happen is that you're going to break this very strong correlation between the photon pairs. And so if you look very carefully at this string, sometimes even when Alice and Bob are selecting the right measurement choices, they still see higher error rate than if there was no eavesdropper. And so one of the important things in QKD is that we assign all the noise from the detector measurement system to the possibility of it being introduced by an eavesdropper, right? And this is actually one of the reasons why QKD is actually attractive as a tamper-evident key distribution mechanism. Now, of course, one of the important things is you need to look at the error rates, right? And we have also worked out that there's a certain maximum error rate one can tolerate. This is about 11%. And it turns out that if you have more than 11% of error rate, when you're doing error correction and compression, you actually reveal so much information during this process that effectively you'll end up with no secret key in the end. And so this is actually an important point to think about. So it actually works. We've been building entangled photon systems in Singapore for QKD for close to 20 years now. In this picture, you're looking at some of the earlier setups where we built this entangled photon pair source, and then we brought it to the rooftops of 2 buildings on the campus. And then we kept one of the photons near the source, and then we transmitted the other one across the campus using telescopes. And then we also did the classical communication to do error correction and key extraction. And it actually worked quite well, and it's especially at night, because QKD is still something that's quite sensitive to stray light. And so we have to do this at night. And you can see that this was running at starting around 9 p.m. And then it worked throughout the night all the way until 7 a.m. when it stopped working. And the QBER actually went up because the sun rose. And so it was introducing so much random signals into the detectors that all you were detecting was essentially accidental correlations. The other thing to note is that the raw key that we were observing is this blue one, and the secret key that we could extract is this red signal down here. And you see these little jagged lines, and there's sometimes when there's some fog or cloud or maybe rain. We get a lot of rain in Singapore, and that actually reduces the visibility, and so the rate will go down. But even with the rate going down, one can actually still extract a secret key. And very interestingly, this is technology that was more than, it's almost 20 years old now. And you could see that even then we were able to extract a secret key, at a rate of about 700 to 800 bits a second. And if you're going to use this, for feeding into an AES system, then this is completely acceptable. So I think, entanglement, technology, especially for quantum key distribution, is something that is, actually quite viable. And we're not the only ones working on it. There's groups in China and in Europe who are also actively pursuing this technology. So I guess just to wrap up, why use entanglement? Like I said, it removes it removes the need for trusted random number generators to be actively included inside your appliances. So we believe that sort of reduces the hardware overheads. If you think of the server model, you can also think of a telco operating the source, distributing the photons, and so it's amenable to third-party operation, right? And finally, we think it's not really a dead-end technology because if you study entanglement distribution, you can also apply it to more advanced quantum networks. And this is one reason why in the university we actually quite like working on entanglement. And so one of the things we're doing now in Singapore is, we're building a quantum safe network. I hope an announcement on this network will be made soon. And the idea is that we would like to, link up the different, organizations that are interested in encryption security and work with them to actually test QKD in Singapore. And in the long run, link up the Singapore network via satellites to other quantum safe networks overseas. So for example, if there's going to be a network built in Abu Dhabi or in the UAE, we would really like to be able to link up the Singapore network with the UAE network through satellites. So I'm going to, take another break here and ask whether there's any questions.
It's a great talk, by the way. Thank you for making so pedagogical. We have some questions here. Sorry.
Yeah, I have one question. So the whole procedure involves sending some entangled photons, measuring, and then sharing the measurement basis with your partner you want to communicate with. So in terms of time scales, how does that compare, like the whole QKD procedure against the less safe classical one?
Right. So I think one has to keep in mind that QKD is not something that's easily done in real time because of the back and forth communication that you do. You can try and compress that time lag or latency if you're worried about it, okay, by doing more advanced error correction techniques. There are some of these one-way error correction techniques that can be used. But I think the important thing to think about is that QKD is a buffered operation. You start the QKD process, you build up a buffer of secret keys, and then you slowly run down that buffer. So if you are using AES-256, then every time you inject a new key, you need to consume 256 bits of key from that buffer. And so as long as your operation can keep up with the rate at which you are depleting the key, then you should be fine. So I think this is an important point. And the other point is, that's why I was saying, I feel that one-time pad encryption using QKD is always going to be a bit niche, simply because of the latency. And so we would prefer to work on this to view it as a buffered operation.
But wouldn't this buffer be because that buffer is then classical, right?
Yes, it's classical.
Vulnerable to attack?
It would be, because you see, again, one of the things I've mentioned is that in QKD, there's a bunch of classical operations that you need to take care of. And so those things must be done in a way that is, safe. So key management is going to be a big part of any QKD network and appliance.
Okay, perfect. Thank you.
I also have one more. So when if I transmit, let's say I transmit information now to, I don't know, somebody I trust, okay? And I do this by the BB84 protocol. And now, of course, if I switch now to the entanglement-based scheme, then I have the server in between, right? And so what happens, or what can I do if I don't trust the server? Do I always have to trust the server in this case, right? Because
So
there's this third party now introduced.
So the third party does nothing to the security, because when you are communicating with your friend, what the server is doing is the server is just providing you with the quantum signals, and then you never communicate classically with the server. You communicate classically with your friend to make sure that your measurement settings are correct, and you do the error correction with your friend, and you do the privacy amplification with your friend. So the server is nothing but a resource that gives you.
So there's no way for the party who is maintaining the server to tamper with this. Also, if let's say I send classically correlated states, there's no way that the server could mess with this in the end.
Let me rephrase your question. The server cannot mess with the entangled state. Right? It cannot clone the entangled state. It cannot
Sure,
copy
no, but it could send a classical state, right? It could just, let's say I hijack the basis of the server and then I send out whatever signal I want. Is then there a way that this becomes unsecure?
You can actually carry out a test of the entanglement.
Yeah, okay, got it. Yeah. So it's really safe then, yeah? Okay, good.
Yes.
Please go ahead, Alex.
Okay.
Thanks. Yeah.
Right. So I hope I'm not running out of time, but let me just go ahead and talk about now how we're going to build this network around the world. And we have range limits with optical fiber. So far in our experiments, we talked about how we did it with telescopes between buildings. And in Singapore, we're going to now launch this national network with QKD signals over fiber. But even then, we have range limits. More than 100 kilometers, it sort of becomes impractical. And so we believe that satellites are a practical way to overcome this. Now, if you're building BB84 systems, or basically trying to build a QKD system where you have to have control over the network, then you can actually trust the satellite as a relay, okay? And so you can actually imagine that you will build a system with a downlink over here or an uplink over here. And in this case, whether it's downlink or uplink, it depends on where that source of transmitter is. If you have entangled photons, you can actually put them on a satellite with 2 telescopes and beam them down simultaneously to 2 ground stations. Of course, you can also think of how to enhance the network by having inter-satellite operations. But essentially, all of these techniques are actually, interesting, and they can be considered as the building blocks of a satellite-based quantum network. The only way to do number 3, of course, is if you have entanglement in space. And so this is something that we are pursuing, and we would like to demonstrate bigger or more effective entangled photon sources in space. And this is where we start talking about satellites and how we're going to put quantum technology inside the satellite. Now, when I started my research group about 10 years ago, we started to think about this problem, and we decided to take the challenge of demonstrating entanglement technology in space. And it turned out that fortuitously, at the same time, there's a new technology from the space sector called CubeSats, or nanosatellites, that was coming out. And to give you an idea of the difference in scale, I show you these 2 photos. On the left is the internal systems, quantum systems for the Mishra satellite, whereas on the right is a model of Spooky 1, which is a complete satellite. It should be able to carry an entangled photon source. It has all the batteries, radios, and computers that will actually operate the experiment. And so it gives you an idea of the sense of scale. And so sometimes people think that nanosatellites are nice to work with. You can build them yourself. They're relatively small and cheap. But I have to warn you that there are also very stringent size, weight, and power requirements that actually, are very difficult to overcome. So one has to be very careful about what you want to do with nanosatellites. And in particular, with this particular Spooky 1 satellite, we didn't have enough volume to put a telescope on it. So what we were doing then was, trying to build an entangled photon source that we could actually operate on the satellite, demonstrate that it works, collect all the data, show that it lives over a certain period of time, and then use this information to design the next step, where we would now have a telescope attached to the satellite. This will probably mean that the satellite will have to go slightly larger, okay, but hopefully it will still be not too large. The other nice thing about using nanosatellites is that they are built to a particular standard. They're all 10 centimeter cubes. You can stack them together to form larger units. And so you can actually, do ride share into space. And this is not something to be scoffed at, because if you have a bespoke satellite, and trying to book the schedule from a rocket, it can actually be very expensive. And so, if you actually could compress your experiment into a small satellite, then you can actually share the rocket launch with hundreds of other satellites and bring down your cost. Now, in our own experience, we found that CubeSats to be actually quite cost effective. Starting in 2010, we launched two experiments on rockets in 2014, 2015. In fact, one of them didn't make it into space because the rocket exploded, but then they recovered the satellite and everything inside was still working. So these nanosatellites are not just toys, they can actually be built to be quite rugged. Then, in 2015, we got funding to build Spooky 1, where we actually put an entangled photon source in. We launched it in 2019, and, it's been operational since then until, just about a couple of weeks ago when Spooky 1 then re-entered the Earth's atmosphere and burned up. And it was operational over that period of time. And now I think we have enough data and enough confidence that we believe that we can actually translate this technology to a slightly larger satellite with a telescope. And this is what we are working on right now. One of the things I want to talk about is how does the satellite actually, would do quantum key distribution. And so the idea is that if you have a satellite flying over a ground station, you will transmit signals to the ground, carry out QKD operation, establish a secret key, let's call that key A. And then you'll do the same thing over another ground station, we call it key B. Now the satellite is a trusted node, it has two keys, and it can actually do an XOR operation and broadcast the outcome, and only the two ground stations can do it. What we're trying to do in our own experiment, the next step, is to equip this transmitting satellite with an entangled photon source, like what you see over here. And the idea is that, you'll keep one of the entangled photons on the satellite, and you'll transmit the other one to the ground. This is a precursor for other more advanced experiments that we want to do where the satellite would actually have two telescopes. But of course, sometimes we get questions about the statistics of signals from a satellite to a ground station, because you can imagine that, the satellite is about 500 kilometers away, and how much losses are introduced in such a system. Well, it turns out that, looking at the best finite statistics estimates that we get from theory nowadays, we find that, a reasonable brightness entangled photon source will still generate about 15 kilobits of secure key on a good pass. And, if you're working in Singapore, we think that there's going to be about 170 viable passes a year. And maybe 1/5 of this will be clear and the sky will not be covered by rain clouds. And so, 20% of them would be viable for QKD. And in the end, you could actually get something like, 510 kilobits of secret key a year. And this is plenty for buffered operation. Of course, the orbit choice is important, okay? You can choose the transmitter size of your telescope on a satellite to whatever scale you want, but sometimes you can think of like a 0.5 meter being the largest thing that's cost effective. The important thing to note is that sometimes, one thing is that if you're in a satellite far away, you actually go over the ground station more slowly because you have a larger distance to cover. But then there's always the diffraction loss, and the diffraction losses are the real killer here. So the further away you go into orbit, the less secret key you generate. And so if you look at, Spooky 1 or low Earth orbit satellites, they are somewhere in this range. You go to geostationary satellites at 36,000 kilometers, you see that there's a slight bump over here. And this is because the satellite is going to be on station all the time. And so it's effectively has very long orbital time and it's continuously transmitting. But even then, you cannot make up for the key rates you can actually generate from a low Earth orbit satellite. And so this is actually, an important parameter to think about. Now, what we're going to do, we're going to, work towards these big networks, but we need to, build a small satellite as the first validation steps of the technology that's inside. And it's not just the entangled photon sources. We also need to validate single photon detectors, which are known to be sensitive in space. We also need to validate the control electronics, and then we have to validate the environmental controls. The satellites are tumbling in space. They present different faces to the sun, so different parts of the satellite are going to heat up. How do you actually make sure that the heat and the thermal stresses are not transferred to the entangled photon source, which is residing inside the satellite? So these are all the things that one has to validate in the first steps. So I just want to make a point. Everyone knows about the Chinese Mission satellite, which is really great. It's validated all the quantum, signals and quantum QKD protocols, and they did everything in a single step. But that was also very expensive. So I think for a small university group, we decided, we cannot compete in that direction. And what we can do is we can try and innovate in small steps. And this is the main idea of Spooky One. Now, the entangled photon source that we put on Spooky One.
Alex?
Yes.
Can I ask you something? So
Sure.
in your scheme, you decide to do, like, if you want to establish a secret key between points A and B on Earth, you first establish a secret key between A and the satellite, and then the satellite and B. And then the satellite sorts the two bits, right? And in the Chinese scheme, they do like the entanglement distribution towards both points A and B on Earth, or is it the same scheme as you use? Do you see my point?
Right. So Missions is very capable. It's got 2 telescopes. So it's validated the BB84, where they act as a trusted node, right? And it's also validated the entanglement scheme. But I have to say that the BB84 one was more successful because they've used it to also do intercontinental QKD. But the reason why their entanglement one was at a very low rate was that they had to make some design choices on the source. And I think that limited the brightness of the source that they had. So all they did was they could actually see the correlations, but there wasn't enough key to generate a final secret key from the signals that they got.
I see. And then in your case, then when you establish the secret key between each point on Earth and the satellite, you're using BB84 at the moment, right?
Yes, but if you replace the BB84 transmitter with entanglement, you have a BB84 variant called BBM92.
Yeah, but then you need to keep the other photon inside the satellite until you measure, or how do you, like,
you don't have
or
to
is
keep
it
it
irrelevant?
That's not necessary. You can actually just measure it straight away while the other photon is traveling down to the ground.
Okay, I see. Okay, thank you very much. Yeah.
I mean, concerning this point, the source for quantum entanglement, quantum key distribution, is on satellite.
Yes.
Okay.
Right.
Thank you, Alex.
No worries. The entangled photon source that we put on Spooky One actually looks like this. We generate, the first pair. Let's put it this way: in entangled photon generation, you always want to look at 2 possible paths for the photon pair to be generated, and then you want to mix them. And then in this mixing process, you should erase the which way information that the photon pair came from. Okay, so you should always think about this. There's always 2 paths, and then we're going to mix them in the end. So the way we did it on Spooky One to make everything nice and compact and rugged was that we had 2 BBO crystals, right, sandwiching a half-wave plate. And they would actually, perform this particular operation where the pump beam is blue light coming in. would generate a photon pair, right? A signal and idler, we call them a photon pair, and then they would actually leave the crystal. Now, as the pump beam goes through the crystal, it's going to do a walk-off, a spatial walk-off, and so the photon pair that's leaving the first crystal would have this elliptical shape. And then in the half-wave plate, the polarization of the photon pair is actually swapped, but the polarization of the pump beam is not swapped. Okay, it's maintained. Now, after this half-wave plate, all the photons, the signal, the idler, the pump, they have the same polarization. And so in the second crystal, they will walk off as well. Of course, the pump is also doing its own thing, producing photon pairs. But now the photon pairs at the output of the second crystal have roughly the same spatial mode, but there's a mixture here. Some of the photon pairs are horizontally polarized. Some of the photon pairs are vertically polarized. And then you erase any phase information that the pump was carrying using this phase compensation crystal. And so in the end, in the output phase, you have this elliptical shape entangled photons coming out, and they share this maximally entangled polarization state. And this is actually an important step, because what we're trying to do is we're trying to ensure that we can collect light over the crystal, right? No matter how the detectors or the collection apparatus is moving relative to this crystal arrangement, right? And so in this way, almost all the photons on the exit phase share the same entangled state, right? And we can actually, we validated this by putting a pinhole in the center and slowly opening up that pinhole, accepting more and more photons. And essentially when you see brightness on this graph over here, what's happening is we're opening up that pinhole. And we can actually maintain very high quality entanglement, right? Which would in turn allow us to generate, a secret key more effectively. So this is the basic idea of what we did inside Spooky 1. The concept looks like this. We have a laser diode that's pumping the crystals, and then we allow the signal and idler photons to expand, and then they fill into 2 detectors. And so this layout is actually presented in this mechanical model. The 2 crystals are over here, the pump lasers over here. We split the signal and idler photons according to their color, right? And then there's 2 single photon detectors over here. And in front of the single photon detectors, we have liquid crystal polarization rotators that can test the basis that the detectors are sensing, and this way look at the entanglement correlations. And so, just to make sure everything is nice and stable, the platform is built out of titanium. BBO is used to generate the photon pair, and the way we generate the photon pair is by tilting, the crystal axis relative to the pump. And so we had to design our own titanium flexure stages. That worked pretty well. So this is the flight assembly or the source with the satellite, right? You can see the different parts, and then it's integrated into Spooky 1 over here. And the rest of it is for the avionics. And, we did a lot of testing, like we shook it. After it's integrated, we baked it in a thermal vac chamber. And the brightness and the contrast of the curves before and after testing were essentially the same. And so that was a good sign that it would work in space. And it did. After deployment from the space station in 2019, we worked really hard to collect lots of data in the beginning. And then, somewhere in the middle of the mission, the radios on the ground, not in space, but the ones on the ground stopped working, and we had to repair them. But after everything was repaired, we still managed to get nice quality entanglement from space. We showed that, over this 600-day period when we're actively monitoring the satellite, the entanglement, was stable. Detectors were still working, the electronics, everything was still working. And so that was actually really nice. It was a really nice validation, because in the future, we can use a lot of the technology in Spooky 1 for more advanced quantum network experiments. And so I just want to end a few words and say that, we're doing a lot of entanglement engineering in our group. I haven't really talked about it a lot, but essentially, we often play with crystals just to look at how we can actually generate this Sigma and idler photons and how we can erase their which way information. And so this is some of the basic experiments that we have tested, right? But more recently, we started to look at designs which look like, this, where you can imagine that there's two paths for the pump beam, and then you can actually combine the entangled photons, because we found that this is actually very stable. And even though this is a periodically poled crystal that requires a 0.1 degree temperature stabilization, is something that a nanosatellite control electronic can actually provide. And of course, looking at this particular model, we looking at these two paths, we also come up recently with a design where we use even less optical components. For example, take the same crystal over here, and instead of splitting the pump beam into two, just expand that pump beam a little bit, right? Let it enter the crystal, and now you can actually, draw a conceptual line, right? And you can imagine that there could be photon pairs generated in the top half of the crystal or in the bottom half of the crystal. And you could just put in a little half-wave plate, right, which is segmented, which rotates only the polarization of the bottom half Sigma and idler photons, and then you combine them with like a BBO crystal, you can actually generate the same entangled state that you see up here, right? And we have validated this, and we're just looking at how to actually, improve, the efficiency of collection, because in the top design, you can actually pump with a really nice beam, whereas in the bottom part, you can imagine that the beam has actually been split halfway, and then you're trying to combine, both of them effectively. And so this is one of the challenges that we're working on, and we continue to work on. But it's quite fun to try and squeeze entanglement or quantum technology into small satellites. So this is the team that actually made Spooky One happen. Where we took a photo on the rooftop of NUS, where we have a Yagi antenna that is used to talk to the satellite. And you can see Rob Beddington, our systems engineer here, holding a real-life model of Spooky One. So with that, I end my talk. And thank you for attending and asking all these nice questions.
Thank you very much, Alex. Thank you for making it so pedagogical and so self-contained, and also punctual, by the way, so great. And congratulations for the fantastic scientific and engineering job that you guys are doing. We have a couple more minutes for some questions. René, yeah.
So regarding the choice of the carrier frequency, I think you work in the optical domain, because there you can nicely generate entangled photons. So I just Googled now, GPS works somewhere at a gigahertz or so, and the reason is, I found, because it can go through clouds. So if you could generate efficiently gigahertz entangled photons, what would be the choice of the frequency of your carrier if you had like free choice, and why?
Definitely we will go somewhere longer. The main reason why discrete variable community works with the short wavelengths is because of detectors. We face severe detector limitations. At the single photon level, the longer the wavelength you go, the less energy it contains. And so it becomes really difficult to detect it against and discriminate against background. So we would really like to go to longer wavelengths. Maybe we don't have to go to gigahertz. If we could go to, 5 to 7 microns or 10 microns in that range, that will already be better than working in the visible and near infrared. But of course, there are some other challenges when you go over there. Diffraction losses is going to be a problem. The longer the wavelength, the more diffraction you have, right? And you got to make sure that your detectors are really efficient.
Andreas?
Thanks for the talk at first. These tiny satellites, would create a huge amount of debris up there. But when they are re-entering the atmosphere, are they completely burnt?
Yes, they're completely
Wow.
burnt.
Okay.
Yeah, in fact, that's a good point. You're actually not allowed to, the space launchers don't want you to launch a small satellite if it's carrying like huge amount of heavy metal, for example, because they're worried that it doesn't burn up completely, and it would actually, hit something or someone when it re-enters. Of course, the chance of that happening is very low because most of the planet is covered by water. About whether or not we're going to face a future where there's going to be a lot of space junk, that's also a valid question. But I think one would probably not generate as much space junk as people who are testing anti-satellite weapons in space. Just a few weeks ago, one we have read about how the Russians launched a missile to blow up one of their old satellites, creating a lot of junk. And the problem there is that the higher you are in orbit, right, the longer it takes to come down. And so I would say, for people who are working with small satellites, it makes no sense for them to go to a very high orbit for a couple of reasons. First one is radio frequencies, right? Your radio frequencies in space are unidirectional. And so if you are further away, you're gonna need more power to communicate with your ground station. Small satellites cannot generate that much power. And so you're going to be limiting yourself in your data. Then, the other thing is small satellites, the idea is that you can understand them, how they work, and then, make use of the latest electronics and the latest designs, and then launch a replacement. So you don't want to fill up space with a whole bunch of old, obsolete, satellites. You want them to come down back to Earth somehow and freeing up the orbital slots for the newer ones. So I think when you think of all of the natural, cost-effective ways to operate the satellites, I'm kind of optimistic that people working in the field will not put lots of them up in the 500-600 kilometer altitude, where they would essentially live for 20, 30, 40 years. And people would begin to populate low Earth orbit with these things that you can replace.
I have a final question, if there are no questions. This is a very basic one. I'm a theorist, so perhaps it's too basic. So when you send light from a satellite to Earth, right, light diffracts, and so the beam waste, I guess that it grows, right? But on that distance, is that negligible, or do you also have to take that into account, the diffraction of light?
Well, we definitely have to take it into account, and this was the point why I showed a slide earlier talking about what is the key rate you can generate when your satellites are at different altitudes. And you can see if you're at geostationary altitude, you actually collect very little light and you can actually generate very little key. It's precisely because of diffraction losses. Okay. But you also want to balance that against your ability to point the telescope on the satellite, because imagine, you have a laser pointer in space pointing at something 500 kilometers away. You're not going to be able to point that perfectly. There's something called mechanical jitter. And so that thing is going to be, there's going to be an offset, and then it's going to be moving around randomly by itself, just because the satellite cannot, point itself that accurately. And so what you do is you try and make sure that the diffraction spot size near the ground station, right, is large enough such that even if the satellite was wobbling, it will cover the telescope at the ground station. So this is something that we think about. And so at this altitudes of 450, 500 kilometers with a 10 centimeter transmitter and a half meter receiver on the ground, we think that's actually going to be sufficient. And of course, the other thing we have to note is that we do all this at night, because at the moment, sunlight will still swamp our detectors.
Right. Okay. Excellent. That fully answers my question. Yeah, thanks. So if there are no questions, it's already, Professor Ling has been talking for like 1 hour and a quarter. So I think it's time to thank him again and congratulate him for his fantastic job. Thank you so much for having been here with us, Professor Ling, okay?
Thank you. Thank you for the kind comments. And it was a real pleasure to share, the concepts and the ideas with everyone. Thank you.